Greetings everyone, Engineer Leonardo here. Well, on this video we'll continue looking at some applications of the Bernoulli equation. In particular, applications more focused on civil engineering, but it cannot be applied to other engineering as well, like chemical engineering, mechanical engineering, and so on, right? So let's go. So the problem we'll be looking at is the problem when you have a reservoir and you're looking at which will be the flow velocity at the nozzle attached to this reservoir. So here's what we have. Here is our reservoir. Okay. It has a certain height of fluid. And here at the bottom, can be the bottom right or the bottom left of the reservoir, we attach a pipe which is long enough, and at the end we have a nozzle right here. Of course, we need some valve to get this flow here. So what will happen, of course, it is full of fluids of certain density, and here we have our height of reference. Here is z equals 0, and it goes up like this. And here we have z equals h, which is the height of the reservoir. So what will happen in this particular case? Think about for a little. Well, when we open this valve here, what will happen? Well, of course, this reservoir we'll consider that is much more larger than this pipe here, this pipe length, and of course much larger than its diameter. Well, its volume of fluid is going to decrease, and it's going to go out right here. We're gonna have a discharge right here. So if we take a streamline of this flow, let's say we have 0.1 here and 0.2 here, right? Well, here we have acting the atmospheric pressure, which is equal to say that its relative pressure is 0. And here, of course, we have atmospheric pressure, sorry, ATM, atmospheric pressure. Well, both on point 1 and point 2, we have the relative pressure equals to 0. So if we take a streamline from 1 to 2, is going to look something like this, right? And here we have the discharge of fluid, and the reservoir is going to decrease in height. Okay. So if we apply the Bernoulli equation between 1 and 2 along this streamline here, what we're gonna get is this. Let me write first the full equation. P1 squared divided by 2g plus P1 divided by gamma plus C1 equals to V2 squared divided by G plus P2 divided by gamma plus C2. Well, as I stated before, the relative pressure at point 1 and point 2 is 0, so we can neglect this term here. Point 2, the reference height for our point 2 is 0, so this term here also vanishes. They are both 0. Well, Z1 is equal to the height of our reservoir, so it's equal to H, right? And of course, the flow here at point 1 is at rest, so its velocity must be 0. Okay, so this term here also vanishes, and what we are left is the following. H equals V2 squared divided by 2G, which gives us the following expression. V2 is equal to the square root of 2GH. If we have the diameter of this pipe here, we have the area, so we have the discharge at the nozzle of this pipe. So the discharge will be equal to, let me go down a little. So let me continue up here. So here is H. So the discharge will be equal to this. Q, which is usually the symbol we utilize for discharge, is equal to A, the area of the cross section of the pipe, times the velocity, which is 2GH. For usually for let me write this as in real life situations in engineering, we often have to include a term to correct this equation here in order to account for losses at the nozzle. Here at nozzle we have high turbulence due to the encounter of water and air. So they're going to be, in the case of course, we are dealing with water flow, but can be with other types of fluid as well, such as oil. Of course, we are all considering Newtonian fluids. But here at the nozzle, we often have some energy losses, so we have to account for a discharge coefficient. Okay, this coefficient here will correct this equation here to account for losses at the nozzle. So this is the general expression of the nozzle discharge in a reservoir. Okay, so here's the correction coefficient. Depending on the losses you have at the nozzle, this correction coefficient can range for about 0.8 to approximately 1. Okay, so hope you enjoyed this class. See you next time. Don't forget to like, to subscribe, and to share this video. Thank you very much. Bye.